Alright, this is section 4.5, which is solving a system using matrices. And the systems that we solve, we're going to stick with 2x2s in this section, but we're going to introduce matrices here. And a matrix, right, singular matrices is plural for matrix, right? And a matrix is just kind of an array of numbers, right? This one is 2 rows by 2 columns, so we call it a 2x2. Right. This is 3 rows by 2 columns, so we call it a 3x2. This one over here is 2 columns by 3 rows, so we would call it 2x3. And these numbers, this 2x2, 3x2, 2x3, that's just the dimension of these matrices. It just tells you how many rows, how many columns there are, right? And these become useful because we can turn a system into a matrix and play with it kind of without worrying about what's happening in the x's and the y's and potentially the z's and w's, q's, r's, s, all those variables, right? So if I have a system, let's say I have some system that looks like this. 4x plus 3y equals 20. And let's say 5x minus 10y equals 11. Right? Something like this. Okay? I can turn this into a matrix by simply taking the coefficients of these values, and I can augment the matrix with these values over here. So I'm going to write my matrix as 4, 3, 5, and negative 10 simply by taking the coefficients off of the left-hand side of my equations. Now, in order to get from the system down to this matrix, I have to have these kind of in order, you know, the standard form of these equations with x's first, y's second, and I don't particularly care so much that my x's are negative or not negative. I just want those values to line up right. And I'm going to augment this with the 20 and the 11, and if I do that, I'm going to make this a straight line instead of a bracket, and then put my 20 and 11 on there, and then close it on the bracket on the right-hand side. And this is called an augmented matrix, right? And I can use this to describe a system. This is this system above. It's the same thing, right? And so we would write any system that looks like this simply as this augmented matrix. Right? Okay. So what can we do with these matrices? Well, let's talk about what's allowed. There's 3 major things that you'll want to do with these. The first thing that you can do is swap rows. Right? If I have a matrix, let's say I have this matrix, I can rewrite it as 3, 2, 8 first and 2, 1, 5 second. That's really just saying, well, I have these 2 equations and it doesn't matter which one I wrote first, right? So swapping rows is a valid matrix maneuver, and it's useful. We'll see that it's useful later, and we'll see why we care about that. But the second thing that I can do is multiply a row by a constant. And I'm going to write by a non-zero constant. Because if you multiply a row by 0, you're just saying, well, just zero everything out, and that's literally taking that equation and throwing it into the garbage. We don't want to do that. But if I multiply an entire row by, whatever number, by some constant, that's multiplying the left-hand side and the right-hand side by the same number. That's just the multiplication principle of equalities, and I'm allowed to do that. Okay? And then 3, the last thing that I can do is add or subtract rows together. But this is essentially the same principle as number 2. If I add row 1 to row 2, I'm just adding the two equations together, similar to how we did in the addition and elimination method, but I'm adding something to the left-hand side and something equivalent to the right-hand side, so it's still that addition principle of equalities, right? And I can do one of these at a time, or I can do 2 of them, or all 3 of them at the same time. And we're going to see how this gets us into the manipulation of these matrices, right? So if we go back for just a minute to looking at how a matrix is formed from a system and kind of go backwards, right? If I have this system, let's just make up some numbers here. This matrix represents the system of equations 2x plus 3y equals 4 and 5x plus 6y equals 7, right? Now, let's look at one more of these, a very simple looking one. If I have the matrix 1, 0, and let's call this whatever, let's say 5, and then 0, 1, and let's call this 6, it doesn't matter what these two numbers are for this example. This matrix represents the equation, the system of equations x plus nothing else is equal to 5, and no x's plus a y is equal to 6. Or in other words, it represents the solution. If I have a 1 in these two positions and 0 in the others, I'm done, right? I have my solution, and this is the goal. This is going to be the goal of this section. How do I turn something like this into this? Well, I use those 3 possible maneuvers. So let's jump into them, let's look at them, and these are, you know, if you've never seen matrix manipulation before, this might be something that you watch slowly, pause a lot, work it out yourself, work along with me, maybe rewatch this video once or twice, but let's dive into it. And I'll show you a little bit of notation that I use, makes, I think, understanding what's happening a little bit easier. Let's grab an example though, one that works okay. Alright, I have a system. I have 3, -4, and I'm augmented with -22. And then I have 5, -2, and 24. And there's a general process, right, that I want to try to obtain, and that process typically starts with me getting a 1 here, right? I have a 3 there, I would like it to be a 1, so I'm going to do whatever I can, you know, swap a row, add multiples of a row together, whatever I can in order to turn that 3 into a 1. So I'm just going to look and reason my way through this and say, well, if I doubled this row, because that's a valid operation, double that top row, that 3 becomes a 6, and then I can subtract the bottom row, because that's a valid operation, and 6 minus 5 is 1. And that gets me the 1 that I want. So writing that down, I'm going to use a little r to represent my old row, and a new r to represent my new row. So I'm going to say double my old row 1, a little subset or subscript of 1 means the row 1, and then I'm going to subtract row 2, and that's going to become my new row 1. So again, my little r's, little r1 is my row 1, little r2 is my row 2, big R1 is my new row that I'm going to create in this maneuver. And I'm not going to touch my bottom row in this first step. So I can write in my bottom row 5, -2, 24. And maybe I can make it illegible. Right? But to do this operation, I simply double the element in row 1 and then subtract the element from row 2, which is to say I'm going to double 3 to get 6 and then subtract 5. 6 minus 5 is 1. That's what I wanted right here, is my 1. But I have to do that everywhere. Double the element in row 1 here is double negative 4 is negative 8. And then I'm subtracting the element in row 2, so I'm subtracting negative 2, right? So that is to say I have negative 8 plus 2, which is negative 6. And that goes in that place for my new row 1. And then I'm going to double the element here, so double negative 22 is negative 44, and then I'm subtracting 24. Right? That becomes negative 68. And that's my first maneuver, and I've gotten the first thing that I wanted. That's a 1 there. Okay. I'll erase my scratch work. The next thing that I want, after I get that 1, as I'm going to use that 1 to eliminate the rest of that column, I'm going to turn this 5 into a 0. That's what I want here, is that. But it's easy to take this 5 and simply subtract off 1 however many times necessary, 5 times, to get to 0. So that is to say, I'm going to not change row 1. Row 1 becomes row 1. But I'm going to take row 2 and subtract off 5 row 1s from it, right? That is to say I'm going to take this 5 minus a 1, minus it again, minus until I get to a 0, that's 5 times. And I don't like the way this looks because I don't like to take row 2, stick it in my head, and then have to multiply 5 times the row 1 and then subtract. So I'm going to write it this way. I'm going to take negative 5 row 1s and add that to row 2 to become my new row 2, right? It's the same thing, I'm just holding off on loading row 2 into the memory banks, because if you're like me, once you've got one number, a 5 in there, you try to throw in 2 or 3 of them and they're like, hey, let's have a party and take off, and they all get drunk and you don't know what you're doing anymore. So I'm going to do it this way. Negative 5 row 1, so that is to say negative 5 times 1 is negative 5, but I'm adding row 2, so if I add 5 back, I get 0. And that goes there. Negative 5 row 1s, so negative 5 times negative 6 is 30. Add that to row 2, so I have 30 plus negative 2 is 28. And then I have negative 5 row 1s. So negative 5 times negative 68, we're going to get a big number here. Negative 5 times negative 68 is positive 340. And then I add on row 2, so I add on 24. So that gives me 364. So they're big numbers for this particular example. I think the example, if they wrote it down below, probably didn't hit these big numbers, but they might have. Actually, I'm looking at it, and they did. They did hit that big number. Right? But in this process, row 1 didn't change, so I'm just going to rewrite row 1. That is 1, negative 6, and negative 68. All right, so that's step 1 and 2. Step 1 is to get a 1 in the upper left. Step 2 is to eliminate the bottom left. Step 3 now is to turn this, whatever is here, into, backwards, wrong one, this one. I want to get my other 1, and the other 1 goes there. Right? And the only way that I can do this, in fact, let's reason our way through. If I try to swap rows, I'm going to mess up the first 2 steps that I've done. If I try to add some multiple of the top row, I'm also going to screw up the step that I just finished. Really the only thing that I can do here is multiply this thing by 1 over 28, or that is to say divide this row by 28, right? And so I will. 28 divided by 28 gives me the 1, that's what I want. 364 divided by 28, that goes evenly, so that's what I want to do. And so this guy doesn't change. That gives me 1, negative 6, negative 68. still. Dividing everything in row 2 by 28 gives me still 0, and a 1, and I want to say that is 10 plus 3 more, 13? Yeah. And I'm actually I'm more than halfway done with the process, but my solution is half here. Y is equal to 13. So I know that right now. The last step, though, is to get this last position to be a 0. So I want to get a 0 there. And I can do that by using this bottom equation, because if I add a multiple of the bottom, I don't mess up the step 1, 2, or 3 here, right? So row 2 is not going to change. Row 2 is going to become my new row 2. But I'm going to take 6 and multiply it by this 1 in order to combine it with this to get 0. So that is to say I'm going to take 6 row 2's and add it to row 1 to become my new row 1. Again, since row 2 is not changing, I'm going to just write it in there. And again, we can still see y is 13. But I'm going to take 6 row 2's and add it to row 1, so 6 times 0 is still 0, plus 1 is 1, and once again I didn't mess up step 1. I also haven't messed up step 2 or 3 because they're already written. 6 times row 2 gives me 6 times 1 is 6, plus negative 6 is 0, and I have exactly what I want on the left-hand side here. 1, 0, 0, 1. Finish it up. 6 times 13 is 78. Added to negative 68 is 10. And I have my solution. X is 10, Y is 13, and I'm done. Okay. All right, let's look at another one. That was some pretty big numbers. I wish it weren't so big on the first example. Let's look at another one, though. This one's not as terrible. Alright, let's start with this system here. 2x plus 5y equals 3. And I have 3x minus 4y equals 16. So the first thing that we want to do, because it asks us to solve this using a matrix, is to turn this into a matrix. So I take my coefficients, the 2, 5, 3, negative 4, augment it with 3 and 16, and there's my matrix. Okay. And then I'll go through those steps. The first step is I want to turn this upper left guy into a 1. That's what I want there. How do I get that? Well, it's easy enough to take row 2 and subtract row 1. So I'll do that. Row 2 minus row 1 becomes my new row 1, and row 2 stays row 2. Right? Row 2 minus row 1, 3 minus 2 is 1. That's great, that's what I want. Negative 4 minus 5 is negative 9. And 16 minus 3 is 13. And then row 2 didn't change, so 3, negative 4, 16. Great, step 1 is done. The next thing I want is this 3 to be a 0, and I can always use that 1 to do that. So I'm going to take negative 3 times this 1 to combine with the 3 to give me 0. So that is to say negative 3 row 1's added to row 2 becomes my new row 2. Right? I'm going to write that down here, because I want row 1 to stay the same. So I'll write it where row 1 goes. So row 1 is still 1, negative 9, 13. Row 2 now, though, is negative 3 row 1's added back into row 2. So negative 3 times 1 is negative 3, plus 3 is 0. That's great. That's what I'm looking for. Negative 3 times negative 9 is a positive 27. Add that to negative 4 is positive 23. Okay. Negative 3 row 1, so negative 3 times 13 is negative 39, and I add that to 16, and I get 23. Negative 23, right? Great, that's step 2. Step 3 is to turn this 23 into a 1. By the time I get here, my options are limited because if I start swapping rows or adding the top row to it, I'm going to mess stuff up. So I can just divide by 23, which is great because this 23, negative 23 is also divisible by 23. So row 1 is going to stay the same, that's 1, negative 9, 13. And then 0, 1, negative 1. And again, we can see that y is going to be negative 1 at the end of the day. Next thing I want is this negative 9 to be a 0, so I'm going to take 9 times the bottom row and add it to the top row. So that is to say 9 row 2's added to row 1 becomes my new row 1. And row 2 becomes row 2. Doesn't change. So row 2 is the same, 0, 1, negative 1. Row 1 becomes 9 row 2's plus row 1, so 9 times 0 is still 0, plus the 1 doesn't mess up my 1. Good. 9 times 1 is 9, plus negative 9 is 0, that's what I wanted. And 9 times negative 1 is negative 9, plus 13 is 4, and I've got it. X is 4, y is negative 1, and that's my solution. Done. Good. All right. I know this is not the easiest thing. I've done 2 examples in like 20 minutes. They do take time. They might take you, that's an average of 10 minutes each for me. They might take you 15-20 minutes for the first couple that you do. So don't get stressed out if it's taking you a while. This is something new, it's something weird. Take the time to do them though. Let's take another example here and I'll work through it a little bit quicker, more quickly. So again, if this goes too fast, don't be afraid to use that pause button and wait until you understand the step until you hit unpause and maybe even try to, guess each step before I do it. So let's look at, let's see. Let's look at this one here. 3x minus y equals 3. And I have 2x plus 4y equals 30. And you might actually look at some of these and say, well, gosh, why would I bother with this? It would be easy to do a substitution method or to set this up for an elimination method. But again, that matrix method is kind of a catch-all. It does all of those things at the same time. So don't look at this and say, well, screw the matrices, I'm just going to solve for y. Yeah, you can do that, but that's not the point of this section, right? Do it in a matrix. If I write this as a matrix, I have 3. This is a negative 1. And then augmented with 3, 2, 4, 30. Okay. I want to get a 1 here, so I'm going to take row 1 and minus row 2. So row 1 minus row 2 gives me 3 minus 2 is 1. Negative 1 minus 4 is negative 5. And 3 minus 30 is negative 27. When I speed up, by the way, this is where all of the mistakes are generated by trying to go fast. So if I make a mistake, I'm sorry, but for your practice, when you start trying to just ramp it up and go quickly, that's where a lot of mistakes happen. So don't always try to go quickly, right? Row 2 didn't change here, so this is 2, 4, 30. I've got my 1, I want to get rid of this 2, so I'm going to take negative 2 row 1's and add it to row 2. That becomes my new row 2. Row 1 is not changed in this step. So that leaves me with 1, negative 5, negative 27 for row 1 again. Negative 2 row 1's, so negative 2 times 1 is negative 2, plus 2 is 0. That's great, that's what I wanted. Negative 2 times negative 5 is a positive 10, plus 4 is 14. Negative 2 times negative 27 is a positive 54 plus 30. It's 94. Right. Ow. Sorry. Okay. Oh, I'm sorry, it's 5, 6, 7, 84. My bad. 84, see? I caught that one. But if you don't catch that and you do 20 more mathematical manipulations, you end up with a crappy wrong answer. Alright. I want this to be a 1, this 14, so I'm going to divide by 14. And so that gives me, row 1's not changing, so it's 1, negative 5, negative 27 still up top. And 0, 14 divided by 14 is 1, 84 divided by 14 is 6. And I can see y is 6. Right? My last step, I want this negative 5 to be a 0, so I'm going to take 5 row 2's and add it to row 1 to become my new row 1 and leave row 2 unchanged. Since row 2 is unchanged, that's a 0, a 1, and a 6. 5 row 2's plus row 1, so 5 times 0 is 0, plus 1 is 1. That's good, didn't screw up my 1. 5 times 1 is 5, plus negative 5 is 0. 5 times 6 is 30, plus negative 27 is 3. And I've got my solution here. X is 3, y is 6, and I'm done. Okay. In all of these examples so far, we were lucky enough to avoid fractions, and there's many ways that you can play around and avoid fractions until a certain point. Let's take a look at this next one where it is impossible to avoid fractions forever, but we can avoid them as long as we can. 5x minus 4y equals negative 1. And negative 2x plus 3y equals 2. Okay. So my matrix is (5, negative 4, augmented with negative 1, negative 2, 3, 2. Make sure I wrote that all right. It looks good. Yeah. Okay. So again, I want to get a 1 here, right? And I can do that by adding on row 2 twice. Because if I double up this negative 2, that's a negative 4. Add it to 5 gives me 1, right? So that's what I'll do here, is I'll take 2 row 2's plus row 1 is my new row 1, and leave row 2 unchanged. So row 2 is negative 2, 3, 2 still. 2 row 2's plus row 1, so 2 times negative 2 is negative 4, plus 5 is 1. That's what I wanted. 2 times 3 is 6, plus negative 4 is 2. 2 times 2 is 4, plus negative 1 is 3. Right? So not too bad. In fact, 1, 2, 3, there's an easy as 1, 2, 3 joke sitting there. I would say I'm not going to make it, but I just did, so too late. The next thing that I want is this negative 2 to be a 0. And so I'm going to take 2 row 1's and add it to row 2 to become my new row 2. Row 1 I'm going to leave unchanged as 1, 2, 3. And then row 2 is 2 row 1's added to row 2, so 2 times 1 is 2, plus negative 2 is 0. Perfect. I wanted that. 2 times 2 is 4, plus 3, 7. 2 times 3 is 6, plus 2 more, 8. And you can see here on my next step, this is where I can no longer avoid fractions. Because the only way of turning the 7 into a 1 without messing up the other two, the 1 and the 0 that I got here, is to divide by 7, but 8 isn't divisible by 7. So no matter what, I have to deal with fractions. I have no choice. But I've avoided them all the way up to this point, right? It's inevitable here, so I'm going to divide by 7. Row 1 doesn't get changed, so that's still 1, 2, 3. Dividing everything in row 2 by 7 gives me 0, 1, and 8 sevenths. Right? And that's why it's unavoidable, because my answer is a fraction. Right? If your answer is not a fraction, if your answers are integers, then there's ways of manipulating these to avoid fractions through most of them. But I can't. I can't avoid a fraction if my answer is a fraction. The next step here, though, is I want this 2 to be a 0, and since I have to use the row below it, I'm going to probably end up messing this one up, and it's going to end up being a fraction as well. And it is. The answers are both fractions. But I'll take negative 2 row 2's and add that to row 1 to become my new row 1. And that's how I eliminate that 2. Bottom row doesn't change. That's a 0, a 1, and an 8 over 7. And then negative 2 row 2 is added to row 1. Well, negative 2 times 0 is 0, but plus 1 is still 1. That's great. I didn't mess up steps 1, 2, and 3 in this step, so I'm good to go. Negative 2 times 1 is negative 2, plus 2 is 0. Fantastic. Steps 1 through 4 are done, as long as I get this guy here. Negative 2 times row 2, I'm going to write this out. Negative 2 times 8 over 7 plus row 3, which is 3. So I might have to think about this one a little bit, write it down, do it. But this is negative 16 over 7. There's no simplification to be done there. 3, if I call that 3 over 1 and multiply it by 7 over 7, that's plus 21 over 7, right? And that's 5 over 7. And that's my answers. X is 5 over 7, Y is 8 over 7, and I'm done. And that's my deal. Okay. All right. Let's look at a couple of other examples. There's 2 more things we want to talk about here. They're very similar to the last 2 things we've been talking about, typically in the first 3 sections of this chapter. Let's solve this system. 3x plus 18y equals 8. And then we have x plus 6y equals 5. Oops, well, this is just a system. Okay. So if I turn this into a matrix, my matrix is 3, 18, 8. And 1, 6, 5. Right? We have that. Okay. So, this is a nice example of swapping rows, because I could take 3 and subtract off 2 of my bottom row, but just switch them, right? I like to cheat my shorthand and just say, bam, those 2 are being switched, right? Otherwise, you might see it like R1 becomes R2 and R2 becomes R1. But I didn't even draw that on the screen, sort of. But I like this little switcheroo symbol. It's pretty quick, pretty obvious what's happening. The top now becomes 1, 6, 5, and I didn't have to do any math, any arithmetic to get the 1 there. The bottom now becomes 3, 18, and 8, right? And then I can get a 0 here. So I can take, say, negative 3 row 1's and add that to row 2 and leave row 1 unchanged. That is to say 1, 6, 5. Negative 3 row 1, so negative 3 times 1 is negative 3, plus 3 is 0. Great, that's exactly what I wanted. Negative 3 times 6 is negative 18. Added it to 18 gives me another 0. That might be an issue, right? Because how do I get a 1 here if I don't have something that I can divide? Let's keep going though. Negative 3 times 5 is negative 15 plus 8, 7, negative 7, right? And I'm stuck. I can't do anything with this. But if you look at this bottom equation, there's no x's, no y's. 0x plus 0y is 0. That bottom row is the equation 0 equals negative 7. And when we saw something like this in the past, that's blatantly false. If my x and y drop out and I have a false statement, what do I have? Graphically, I have parallel lines. My solutions, there aren't any. And I'm done. If I zero out one of these rows, but I don't zero out the augmented part of it, I simply have no solutions. And again, these are parallel lines. Right? All right. Let's take a look at the next example. You'll never guess what the outcome of the next example is going to be. Kidding, of course, you probably already have. 2x plus 3y equals negative 4. And 6x plus 9y equals negative 12. Okay, so if I write this in a as a matrix, right? 2, 3, negative 4, 6, 9, negative 12. Okay. Now if I come across this situation where I have a 2 and a 6, it's very difficult to make a 1 out of those, right? Because no matter how many times I multiply this 2 by a nice whole integer, I'm going to get something that's even. And it's hard to take the difference between two evens and get a 1, right? And so if this happens, rather than trying to get this 1, right, we would typically say try to get this 1. If you can't get a 1 there, skip it and get a 0 here first and just go around that little clock starting at this bottom left instead. So I'm going to get a 0 here, and then I would get a 1, a 0, and then I'd come back at the end and get my 1 there, right? So that's what I will do here, is I'm going to skip this step and say, well, I can get a 0 here, so let's do it. And I can do that by multiplying the top by negative 3 and adding it in. That is to say, negative 3 row 1 plus row 2 is now my new row 2. Right? We're not going to get very far in this. We're not going to go around the clock because we're going to run into an issue here. But if row 1 isn't changing, this gives me 2, 3, negative 4. Negative 3 row 1, so negative 3 times 2 is negative 6, plus 6 is 0. That's great, that's what I wanted. Negative 3 times 3 is negative 9, plus 9 is also 0. Shoot, darn it, there's an issue. Negative 3 times negative 4 is positive 12, plus 12 is 0, right? So I've zeroed out the entire bottom row, but again, 0x plus 0y is then equal to 0, that's true. And if we talked about this graphically, this is two of the same line, which means I have infinitely many solutions. Infinitely many solutions. And we could have guessed that by noting that the second equation is simply the top equation multiplied by 3, right? 2 times 3 is 6, 3 times 3 is 9, negative 4 times 3 is negative 12. It's the same equation. It's the same line, right? So That's our last example here, is if you completely zero out a row, that's always true, no matter what, and therefore you have infinitely many solutions, and you're done. All right. Thank you. Hopefully that helps. Works through these. There's some homework problems, of course, so do those and take your time on them. These ones are not the easiest things in the world, but they are valuable later on in further math classes. So thanks. I'll see you for 4.6.